Maybe thorium and lifter was once a concept, challenging the troubled fission industry. Now it is a public relations gimmick to proliferate the building of unpopular, cheap, and untested uranium-plutonium cycle reactors. This program uses regulation to concentrate wealth for energy company executives and concentrates power for politicians with weapons manufacturing campaign funds. I'll go into the specifics of thorium lifter on the next slide. So what do you do when your business is a lie, when it is neither cheap nor safe nor non-polluting, when the only way to break even is to make weapons which threaten humanity's existence? Well, you cut costs and you produce propaganda. Cutting the costs include taking chilled work environment at the Tennessee Valley Authority, where the plant was fined because plant workers were fearful of termination if they pointed out safety concerns. These same workers have now had their union broken. Now such troubled plants are being pushed to self-regulate. Think of the money they'll save by not having those pesky inspections getting in the way of maximizing their profit. Cutting costs include reclassifying high-level radioactive waste from Savannah and Hanford and also nuclear plants as low-level wastes. This will save the weapons and power industries an estimated $40 billion and increase the likelihood that people will be exposed to these horrific toxins. There is $1 trillion plan under both Obama and now the Trump administrations to upgrade nuclear weapons. This involves making more of them and also making types which are increasingly likely to be used in war. It would be difficult to do this without new plants coming online, as those existing plants are largely unpopular in their communities and closing for various reasons. While the existing plants have the potential for horrific failure, they usually don't fail catastrophically. This is largely due to decades of safety implementation with large and small leak safeguards, testing and experience on water-moderated shielded reactors. However, the Department of Energy is throwing all the safety along with the waste guidelines developed with experience in favor of novel and unproven reactor designs. The old designs are expensive and simply can't compete with renewables. Renewables are disruptive and are allowing new players in the energy market. The more power that comes from renewables, storage, and efficiency improvements, the more the power companies have to charge their remaining customers. This drives the economics to these diverse players who are competing successfully in a dynamic market. There are no small players in nuclear energy due to regulatory hurdles inherent in uranium and plutonium handling. Their solution is to make cheap nuclear plant designs, throw out waste, and address novel safety concerns with public relations. Enter a change in the relationship between the uranium plant industry and thorium proponents. That's where the propaganda comes in.
Greetings, Thorium Focused. I would like to explore the negatives of the thorium molten salt and liquid fluoride reactor proposals that have been so positive on YouTube. There are great disadvantages with these systems, to the point at which I'm asking why are there so few counters to these proponents? Please join me in taking a skeptical approach to thorium-powered reactors, as much has been left undiscussed on this subject. First exposed to thorium proposals around 2009, I have since followed the changes in those reactor designs, and 10 years later, I have some observations and also some questions. The first is in who bears the cost and who gets paid. If it's so great, why, after holding on to the last remaining stockpiles of uranium-233 for over 40 years, did we then go and destroy them? I would also like to point out major problems with safety issues, today magnified by the risk inherent in nuclear power. and how that probable cost is to be shared. It may be useful to look into monetary pressures causing the most recent disasters, such as an update in Boeing's 737 new optional safety features and the Deepwater Horizon speed up. These caused the deaths of hundreds and a major cleanup. The building of the reactors at Fukushima were met with great protest in Japan, as the population has a vivid memory of the bomb attacks. Despite popular opinion, monetary issues trumped democracy, and that plant was built with assurances that it was absolutely safe. My history with nuclear reactors starts in childhood, and Lewis Strauss's "too cheap to meter" quote repeated over and over by our power company representatives. They were given a platform at my grade school as they pushed nuclear plants on a largely uninformed public. Safety was a given. They explained that the reaction for power generation was very different from the reaction for a bomb. My first physics course at university was taught by Pete Gibbs, an ex-Navy man who explained the reactor tubes and that upscaled civilian reactor to his boss. Well, they would prematurely fail due to neutron bombardment. Asked yet unwilling to change his mind, he was fired, and he became a university professor. I became a molecular biologist, sequencing DNA in inherited diseases and cancer. I say 1,000 times no to thorium. I will attempt to address the misinformation I have discovered and put in the changing context of alternatives. Lastly, I'll provide some perspectives that are avoided by thorium proponents. Please leave your clean and non-offensive comments below. Please follow the links in the description below, and well, leave your own. So I will try and break down the falsehoods in the argument as to what are the properties of thorium that make it, well, just not so great. We'll also look at the reactors and take a few digs at the proposals and concepts, as this has limited real-world experience, and it is shifting and relatively unknown. We'll also look at timeline and how long and how much it would take to get thorium and U-233 reactors working. We should also consider the state of the nuclear industry, the claims, whether they're in good or bad faith, and whether it can be turned around. We'll also examine risks, novel views on proliferation, safety, and how they plan on working with regulatory agencies, and the recent historical perspective on profit, public interest, and risk. Lastly, we'll take a look at alternatives and the items that still need engineering and experimentation, and whether our attention would be better spent elsewhere. Thorium just isn't at all like fissile uranium-235. It's fertile, like uranium-238. The relative amount of thorium in the Earth's crust is at 6 parts per million. Uranium is 4 parts per million. Some sources put this at 3 times more abundant, and perhaps it's easier to extract, but it's just not that different. If you mined pure thorium and put it into a reactor, nothing would happen. A portion of it would need to be converted to uranium-233 through neutron bombardment, an energetic and very expensive process before it could be used to sustain a nuclear reaction. Uranium-238 is similar, except it is largely viewed as a contaminant to uranium-235. However, this fertile form of uranium is already sitting around and is readily available. It is so cheap they may even pay you to take it away. It can also be bombarded with neutrons to make it fizzle as it converts to plutonium, which can then be used in a reactor or become preferred bomb material. We should compare the abundant fertiles, thorium, with uranium-238. Similarly, we should compare the fissiles, uranium-233, uranium-235, and plutonium. Current proposals are all breeder proposals, reactors which create more fissile material if they breed in a ratio above 1.0. For thorium, theoretical breeding maximum is at 1.2, with an experimental suggestion of 1.01 at shipping port. However, an experiment at the BN1 reactor achieved a ratio of 2.5 with uranium. There are no significant stockpiles of uranium-233 to make pure thorium reactors. To make any significant quantity of U-233 at a reasonable cost, one would have to use uranium-235 or perhaps plutonium as a neutron source. This would take many years to create enough uranium-233, separate and enrich it before you would have your first pure thorium uranium-233 reactor. Starting with one uranium-233 fueled reactor, one could double the number of reactors with thorium every 20 years or so. So with pure thorium U-233 cycling, one would have 32 power plants in 100 years, not counting the initial creation of uranium-233. The result would be 6.4 gigawatts at 200 megawatts each. That would only be about 1/4000th of today's energy usage. The feasible way to make enough uranium-233 from thorium is to use a seed and blanket reactor with U-235 as the neutron source and thorium as the blanket. This maintains the status quo for the foreseeable future, generating power and creating waste and bomb materials in conventional uranium-235 plutonium cycle. If the lifter can also provide this breeding environment, as suggested by many, it also provides no great incentive to move from the uranium-plutonium cycle until uranium is sufficiently expensive. Current reactors generate 1/3 of their power from plutonium fission, which would also be used for bomb making. Lifters could likely do the same. The comparison on YouTube of low-enriched uranium to platinum is false. Reactor-grade uranium is less than 1/50th the cost of platinum. The real costs of nuclear power are in insurance, decommission, financing, and building a reactor. Its design and testing are also very expensive. Fuel is only in the millions. The rest are in the billions. This is an image of a breeder reactor proposed by Bill Gates, starting with a fissile core, burning up uranium-238. It starts out very simple and promises to produce, yet contain many transuranics. While conceptually simple, I believe this will produce the worst wastes yet, and would become in reality a complex and hazardous reactor. I would oppose this more than thorium. Okay, that's true. I give it 2,000 times no. While the products from thorium are less lethal than that from uranium, they're still using uranium in the near term, perhaps in a mixed salt, which would have all of the products from conventional fission, plus a few new ones. Alternatively, one could use a seed and blanket design, still making standard wastes. The pure uranium-233 thorium reactor will still make long-lived wastes, including protactinium-231, which has a half-life of over 32,000 years. The molten salt reactor was a mixed waste cleanup that was both very difficult and nearly had a major accident. There are still products which need constant maintenance these 38 years after the small project. Germany's THTR-300 thorium U-235 mixed prototype reactor was significant in size, but was taken offline due to unforeseen issues and remains both too hot and also unfunded to clean up. Thorium as a fuel has been given many chances, including being tried in 15 reactors to date. It did show some, albeit minuscule, breeding potential at shipping port. The great thorium conspiracy seems to run away from this fact. The history of projects doesn't look successful, and the only pure thorium reactor currently producing electricity only makes 30 kilowatts, that's with a K, or about 1,000th or less than what is needed for a nuclear submarine. Like the molten salt reactor experiment, a lifter could also be readily adapted to using uranium as a power source and could forego thorium altogether. So the reality is that we need uranium-235 in reactors if we want to breed either U-238 or thorium. One could adapt a lifter to U-238 breeding by using less graphite to speed up neutrons for fast breeding. Perhaps one could also design a kidney to remove plutonium for bomb making. Criticism of lifter is problematic mostly because, as we learn of inherent problems like protactinium, which lowers the breeding efficiency, the plans change, and then the analysis changes. We are seeing that even an experimental reactor will be expensive, and novel plants outrageously so. There is a common proposal to produce new conventional plants in a factory for distribution. This would result in smaller, say, 200 megawatt plants in many more locations than currently. Given a common design flaw, it could impact many more places at once, and one could foresee cover-ups to initially label design flaws as user error. Some lifter proponents suggest the design prevents proliferation, but as discussed, the uranium-plutonium cycle can be used to make bombs in the same reactor. The molten salt reactor experiment had many issues, as would be expected with an experiment, and didn't explore breeding, the alloys needed, protactinium removal, increased output, what would happen with scaling, gas cooling, melt plugs, and etc. Designed safe can be said of every reactor that has been sold to the public. While this is the most recent, it is also largely unproven. This is also to be put in context of the power industry, which is anti-government, anti-regulation, where lies are endemic, profit is placed above safety, and it enjoys international status to the point of suing nations for threatening profits in ISDS. Now they wish government funds for all stages of research, development, finance, and insurance. This is a big push with other people's money. The profit part they understand and prefer to handle privately. Lifter is a shifting concept at this point, some as issues are discovered and solutions proposed. However, there is fog on exactly what is being proposed and who it will benefit, what it will cost, and who it will threaten. This is a slide of a lifter chemical processing proposal to aid a thorium reactor in breeding uranium-233 by removal of protactinium, a neutron absorber. This is no longer a simple closed system that gets fueled once in 30 years. It begs the question, could one remove bomb materials with a similar apparatus? Thorium's supposed proliferation resistance is often cited as the major barrier to its adoption as a fuel source. This is no longer true. If uranium-233 is bombarded with enough neutrons, one could produce uranium-235, a fine bomb precursor. Of course, if you are using a mixed fuel in a lifter with the chemical processing loops, perhaps bomb making would be even easier. Earlier sealed thorium-only reactor proposals stoked the anti-proliferation claims, which are repeated in these circles. However, the profit motive isn't immune from false claims and gaining support from anti-bomb advocates while betraying the very idea. As the profitability of nuclear power diminishes, the need for revenue from other streams increases. With the great need for state funding at all stages and state actors' desire for the ultimate threat and protection of nuclear bombs, the greater the likelihood of bomb material production. Lifter and thorium is a Trojan horse for nuclear weapons production. This slide depicts a metric ton of thorium being magically converted in a lifter to, among other things, 100 kilograms of uranium-235. See the red arrow. 10% U-235 would be considered well enriched and, of course, is a possible bomb material. It could also be used to transform U-238 to plutonium in another reaction. The last reactors being built in the United States are at Vogtle, using a relatively known AP1000 design. It is currently way over budget, having received $12 billion in federal loan guarantees, with current cost estimates for reactors 3 and 4 of $27 billion. Insurance reserves are only at $2 billion, which wouldn't cover many foreseeable incidents. Instead, it is covered by the federal government, the taxpayers. The on-site contractor Shaw is known to have dropped a major subassembly and covered it up for some time. This disregard for safety is unfortunately common, despite the great risk of plant failure. Quarterly profits and long-term plant use form a bad partnership here. The quarterly profit and stock portfolio optimization are also at odds with safety and storage security. So, what will the development of a new reactor design cost? As more issues are known, the costs only rise, so previous estimates only serve as a lowball. We know a proposed system at Fuji failed to move forward, despite a modest $300 million price tag. However, the process was able to generate patents for many things, a cost to use or a limitation on profits for new entities entering the market. We do know that those proposing this operation have the burden of providing estimates and breaking down costs. The last point here is also that it isn't entirely novel to make a reactor without primary water cooling. However, most such designs have been abandoned, most deemed dangerous. The old molten salt reactor design was pursued for some time. However, poor breeding due to protactinium buildup caused the design's abandonment. The design also had issues that might impact a novel design of lifter. Of note is that the control chains fell apart, likely due to the salt, heat, and/or neutron bombardment. While there are proposed alloys to deal with the harsh environment, there is little that is proven, though I have heard of experiments to explore this. Alvin Weinberg also suggested safety of a reactor was most assured by a smaller size. The experimental molten salt reactor fell into this category. However, proposals for much larger reactors failed the earlier residual heat cautions of Weinberg. The cleanup from the molten salt reactor experiment was called the most difficult to date by contractor Bechtel. It took 40 years and a near-critical incident. There is still contamination in the tanks. Embrittlement of the containment was noted despite the short time and limited output. We also know that the lack of water in the reactor increased the safe working distance as the shielding was reduced. This, coupled with very high temperatures above 600 degrees centigrade, should make maintenance much more difficult. While I'm certain nuclear engineers could come up with interesting designs, our problems come with building, testing, developing, and installing in today's market. The few problems listed arise in an industry which has shifted in the gig economy to short-term, marginalized labor, supply chains with overrated materials, and questionable standards. Fly-by-night companies are the way to get things done cheaply and unfortunately wrong. We are now finding that despite the promises, most reactors leak, and given the 450 reactors in the world, there is both a history and pervasive risk of major accidents. As stated earlier, sold as safe applies to all reactors sold to the public, including Fukushima. While we count on our engineers to approach the foreseeable problems, there are also the unforeseeable issues that are unique to location and, of course, circumstances such as funding and maintenance. Touting a design as walkaway safe before a prototype is built can be very unhelpful. Picture the job site when someone finds a flaw and is fired for troubling superiors for an issue when the reactor is known to be absolutely safe. The flaw may be addressed eventually, but there will be fewer whistleblowers. Problematic contractors or designs that are difficult to upgrade have multiple examples in nuclear history. The problems at Saint Onofre and the steam pipes and their retrofit that ultimately shut down the reactor is just one of many examples. The anti-government, anti-regulatory energy sector is a constant storm of lethal and disastrous continuity. While the NRC has reined them in a bit, the strain of limited profits has compelled the economics to cheat on safety. The industry does have a fight against safety standards and will always find that more profit could be had if safety controls could be subverted. The energy sector has developed considerable clout in politics to influence regulation for its advantage. While most nuclear plants were designed for 40 years of operation, most plants in the United States have been extended their operation for 20 years, and there are proposals for another 20 years for some. Despite safety assurances, 3 plants have closed after receiving extensions. Indeed, there is an aversion to closing plants as postponing the multi-hundred-million-dollar cleanups are very beneficial to the bottom line. Corporate restructuring is frequently used to declare bankruptcy and leave the government or public to pick up these huge decommissioning costs. This is a basic lifter or molten salt reactor with a walkaway fail-safe design. It is running between 600 and 900 degrees centigrade using a heat exchanger producing about 200 megawatts. If power is cut to the reactor, the heat exchanger pump stops working, but so does the safety fan. This allows the emergency melt plug in deep blue to melt, dissipating the fissioning seed into the gray capture vessels, stopping the reaction. Of course, on the job site, a panicked manager might want to extend an outage and bridge the fan until a solution can be found, as it may be quite a long and expensive process to recover the now solid seed salt and restart the reactor. Here is the same reactor design after a given common threat, a flood, as most reactors are on water sites, some with earthquake tsunami potential. The melt plug must be below the reactor and as such would remain cooled not by the fan but by an inflow of water. There would be no release of fissioning seed into the dissipation tanks. If the accident took out the power of the heat exchanger also, it would not be functioning and the dumping of 200 megawatts of heat would be held in the reactor. The increased heat of the reactor in contact with the water would create steam and, if high enough, a hydrogen bubble. Said hydrogen bubble is what blew apart the Fukushima plant. The reasons lifter is at best a long-term proposition include: while the molten salt reactor was not definitive, there's much to work out as far as the reactor is concerned. China has reportedly pledged over $3 billion to start work on some prototypes. While that seems like a lot of money, it may well be less than the cost of a modern power plant and can be considered lackluster in light of China's growing power demand. Additionally, in the United States, there are other novel modular U-235 reactors on the drawing board that are favored for manufacture and strategic placement around the United States. They are not designed to use thorium. Due to our experience and concerns with safety and the increasing costs of nuclear power, especially plant construction, research on novel designs has largely been stalled or bypassed. Lastly, the time needed to procure sufficient quantities of uranium-233 is a layer of complexity in reactor designs which must be made initially to burn uranium-235. This would push the timeline out probably until U-235 comes into short supply, at least 80 years or so. Lifter designs fail to address many of the current problems with nuclear power. The economic model is the same. The long-lived wastes largely remain an externality, a cost incurred but not shared by those who profit. Regardless of whether it can be used for bomb making, the waste would be a problem for the future, past the predictable time for our current geopolitical structure. So what are the real costs projected with thorium? Firstly, there are the externalities common to the energy sector: untracked health and environmental impact. Second, we see a demand by many who are free marketers demanding the government to fork over billions for their pet projects, provide research, billions in loan guarantees for many years of financing and plant construction. Outrageous amounts of liability are also borne by the government and public for major nuclear accidents. It is worth noting that government liability incentivized the banks during the economic collapse, as it was something that could be gamed for short-term profit. Likewise, the government holding the guarantees against calamity could also be gamed by these players. Finally, the investment in thorium can be seen precluding investment elsewhere, as there are many needs which could be considered more important. The effect of ionizing radiation on DNA is relatively known. While the radiation origin portion of inherited disease is not known, inherited disease is a continuous, significant cost that will likely to continue and increase. Other than the male's X and Y chromosomes, we each carry 2 copies of each gene, allowing us to be outwardly normal, even if we have a defective gene, as long as there's a functional gene on the other chromosome. Increasing mutations in egg and sperm cells can raise the likelihood our offspring will have increasing genetic anomalies for all foreseeable descendants. Then, of course, there's cancer. Cancer epidemiology is relatively expensive and usually requires state funding. Proponents of nuclear energy say it has caused fewer deaths than other energy sources per watt delivered. However, the numbers are very fuzzy. We see that just due to traumatic deaths and acute radiation syndrome, there were only 37 deaths from Chernobyl. But it also seems like an extraordinary number of those who dealt with the cleanup have come to an untimely death. So while we know that 37 deaths is not likely giving us the whole story, it may be difficult to know just how many deaths have come from the Chernobyl disaster. We also don't know how many cancers have arisen from any nuclear disaster, much less people have had their germline mutated from nuclear developments in the United States. We do know that nuclear power plants leak radioactive waste across the country and around the globe. Fukushima alone spewed waste carried in winds all the way to New England. Many find there is immense profit in an industry which has an inability and is unmotivated to ascertain the harms it has caused and to whom. These are the known modes of damage to DNA from ionizing radiation. The effects can be greater depending on where they take place in the genome and which type they are. They can frequently be found in germline sequencing, but causal mutations in cancers are much more difficult to ascertain. While mutations causing cancer in somatic cells such as prostate, breast, lung, pancreas, etc., can cause death in individuals, germline mutations cause disease and death in all known descendants. For example, certain BRCA1 and 2 mutations are proven to cause cancer in all women past a given age. If egg or progenitor sperm cells become mutated in this way, those effects may be devastating for a family line. For example, a pregnant woman's embryo can be impacted by radiations in its progenitor sex cells. The damage could be expressed only in a portion of her grandchildren, only later in life, after which it has already been passed to all subsequent generations. We only understand the function for less than 10% of the genes in the human body, and are just getting to understand transcriptional control and epigenetics. There are close to 3 billion bases of DNA in each one of our cells, most of which we are uncertain of what would happen if they were to be changed. Our inability to address long-term waste given over 60 years of production makes proposals to increase nuclear use absurd. The proposal to store waste in Yucca Mountain was rejected by Nevada. They don't want to have everyone's waste rolling across their roads and rails. Would you? Also, with accidents, there is radioactivity that predictably gets released into the local environment. The amount can be stunning, as we see with the growing contaminated water storage at Fukushima. The debate on what to ultimately do with this waste should consider the human desire to use poisons on our enemies. Perhaps we are our own worst. Thorium isn't the only way, even if you want to do nuclear. There are the fusion projects. The fuel is more plentiful than thorium, cheaper to obtain, and near limitless. We know the reaction works, as plain as the sun. We just need to develop a reactor which breeds just a bit more power than it consumes. In today's terms, one should look at current technologies to see costs without subsidies and what may be done to provide dependable power safely at a good price. We will take a look at the cost of nuclear and alternative powers and discuss it just a bit. There are dynamics with storage technologies which would make newer sources more attractive. ITER is a fusion project which is international in scope and is generally regarded as non-proliferative. It has the support of many nations and has a similar timeline and outlook as thorium. If it works, it promises to provide huge amounts of energy cheaply with no catastrophic consequences. Unsubsidized pricing shows the current leaders in power plants coming online are wind and utility-scale solar in price per watt. Nuclear power is rising most sharply, now 3 times the cost of wind and utility solar. This is more of the same information. It also shows that rooftop solar is the most expensive, but may compete with nuclear. Rooftop has the potential to disrupt the power monopolies, but likely would need support from building codes or the like. It would also need storage to make for grid-free living. Gas peakers are even more expensive than nuclear, but they quickly add power to the grid as needed. This slide shows the rapid decrease in battery storage costs, now competing with gas peakers. Since the cheapest energy is periodic, a reduction in storage costs can make these energies more dominant in the market. There are additional storage options which could use engineering and development to realize their potential. Compressed air storage might be practical for short drives, a single house, or even an entire community. It may be cheaper and have greater longevity than batteries. The air could be stored in carbon fiber vessels of a few liters or in underground formations of enormous size. Hydrogen is generated by excess wind at Falkingen, Germany, in the low megawatt range to displace natural gas. This removes transportation issues and storage. If captured separately, it could be used in fuel cells for much lighter electric cars or in future aircraft. Thermal and molten salt can keep energy stored in it from the sun or from the grid for significant periods. Thermal plants already exist in 2 gigawatts of capacity, others that hold significant capacity for an entire season. Whether one boils water with molten salt immediately or later matters little. It has a wide temperature range and can maintain high efficiency up to a week at a time. Flywheel storage can be compact and very responsive for load balancing on the grid, while frictional losses make this just a short-term option. However, it should have a greater lifespan than batteries. Rail energy storage is a simple concept wherein a rail car is filled with heavy material and run up an incline when power is plentiful. It uses regenerative braking when power is needed on descent. It leverages off-the-shelf components, and there are prototypes being built. A heavy rail car on top of a hill with the brakes on can hold all of its potential energy indefinitely, or upon release, convert it to electricity quickly. Pumped hydro is efficient, mostly limited by location and grid layout. One needs 2 water volumes of differing heights. Excess battery storage from electric cars has been proposed to meet demands during peak times. Charging could be done in times of less demand. Owners could be compensated for their use or just evade peak grid pricing. Lastly, there is the plan to shift energy-intensive production to times of highest output. Incentives or pricing options could make this attractive to energy-intensive industries. Thorium already has a long history of failure being tried in many power plants and projects. It is only a bit more plentiful than uranium. All the thorium in nature is non-fissile and unable to power a reactor. The only way to commercially convert thorium to its usable form is by using conventional fission of uranium-235 or plutonium. The proposal to make uranium-235 from thorium-based lifter is most concerning. It shows a clear path to nuclear weapons proliferation. Frequently proposed for lifters is the insertion of long-lived transuranics for burnup. Of course, standard uranium fuels could also be used and would not be precluded. While the frailties of boiling water reactors are reduced, new dangers are introduced. It will not be developed in time to compete with the rollout of small modular reactors now popular with power companies, but not with the public. The public does not want a nuclear-powered future. Investing in lifter research precludes using the funds for childhood education, medical research, or the much more promising power alternatives growing around the world. The waste generated from the transition could be much worse than the current waste we haven't addressed despite the 70 years given. The dangers to us are in cancer and hereditary disease. The impact would be long-term as to include all foreseeable generations. The risks from radiation include many unknowns as the political football has been passed. I would also conclude it is impossible to separate incentives in the nuclear industry with weapons manufacture. While there are immense short-term profits, they are dwarfed by the outrageous foreseeable long-term impacts 1,000 times. No. Thank you for joining me on the adventure. Please visit the references below. Please also feel free to comment non-offensively and germanely with references, and we can see if facts change minds after all.